Okay, so we just continue on with a similar topic, or at least the application is the same. And Peter Jan van Leeuwen will tell us about sequential Bayesian inference in the geosciences.
Yeah, so first of all I'd like to thank all of you still being here and the organizers for having me. I'd like to point out all these people that found me and of course the people that did the real work. Let me see, okay, so motivation, I want to do Bayesian inference, and in my case it is state estimation in this kind of, not this kind of system, I can assure you.
It's going.
Oh, it's going, okay. So what we show here is what I show here is, good point, right? So this is Africa, these colors here are the size of the velocity at about, what is it, I don't know exactly, 200 meters deep, I think, in the ocean. This is a model simulation, and so what you see here, it's highly variable, and this is an ocean model with about the order a billion variables, and we want to do state estimation on these problems. So this will be uncertainty quantification, not in capitals, because I'm not using an emulator, or because I don't know how to do it on these systems. Of course, if you know, please tell me. So the way I'm going to do it, I'm going to use particle filters, because you've seen this is highly chaotic, turbulent, highly nonlinear, and we know that the Kalman filters, etc., they just miss out too much of what's going on. We really need to go to more nonlinear data simulation or Bayesian inference method. So data simulation is Bayesian inference for the geosciences. I think that's sort of fair. Okay, so I'm going to use a particle filter, and I'm quickly I'm going to try to explain what that is. So the idea is we have a probability density function, and in some way we generate some samples from that. And these are my samples, and these are the samples, the blue bars. The bars are equal height, meaning each of these samples has the same weight. They're all equally likely. For instance, because I did draw them randomly from this distribution. And typically you propagate. So each of these samples is a full model state, right? So it's this billion-dimensional state, and I propagate this whole thing, so all these different ocean model states forward in time with my ocean model until I have observations, and so there are my model states, and these are my observations with the uncertainty. So I've depicted here the likelihood in state space, and then what the particle filter does, it just re-weights. It gives particles a weight dependent on how close they are to the observations, more or less. And so we've reduced the weight of these guys, their weight will be very close to 0, and these guys get much higher weight. So that means that if I calculate the mean, for instance, now over the ensemble, it's really dominated by these guys, and these guys don't do anything. And that is actually already a problem with these particle filters. You see, I've sort of lost the majority of my particles. I started out with 10, I've lost 6 of them already. And so, the way we say for small ensemble size, what we can run is of the same order as from the last talk, order 50 to maybe 100 to maybe 500 particles, or ensemble members, or ocean models. And I don't know, so forget about bias here, but anyway, so the whole thing is that we say that the particle filter is degenerate. We just lose the majority of the particles. And in reality it's actually even worse than this. There's only one particle that gets a reasonable weight, and the others get weight very close to 0. So mathematically, we can understand this. We use Bayes' theorem. X here is my state. X is my state vector. Y are the observations. I'm trying to find the representation of this posterior PDF, and we use standard Bayes, of course, and I have my particle representation of the prior, and then if I just plug this into that, then I see that my posterior is just a weighted set of particles, and the weights are equal to the likelihood. So observation given each of these model states, and just to give you, to hammer it home for those of you who still decide what's happening, so suppose that the errors in my observations are Gaussian distributed. So I have this big observation vector here, and I'm just comparing the model equivalent of the observations with these. So I make observations in my model and compare them to the real observations, and then I just calculate these things. So I know what these weights are. I can just calculate them. It's extremely simple. So that's all. It's extremely simple data simulation method, and the problem is, of course, again, when the number of independent observations is large, and large means, let's say, larger than 10, then the variance in these weights is enormous. And the number of observations we typically have at every observation time is maybe, I don't know, 100,000, million, a few million. So the question is, what can we do? How can we make these particle filters useful? Because clearly the standard vanilla version doesn't work. And so the community seems to move into these three directions, and so I'd like to quickly show you what we're doing. One of them is, the first one is a thing called localization, and I can try to explain that as follows, that if I have an observation, let's say here in the North Atlantic, to what extent should that observation influence, that's not what I wanted, let's go back, should that influence this area over here, close to Indonesia? So physically you could say, well, there might be some direct interaction, but it's really it should be tiny, right? There is no direct physical connection, or if there is a very, very small one, between what happens there and what happens there at a specific time instant. So this observation, so this part of the ocean shouldn't really see this observation. But of course, the way the weights are calculated, you get one weight for the whole state, using all the observations in the whole domain. And actually it turns out that in geophysics quite often we don't have to do that. We can do something that we call localizations, meaning that in each grid point I'm only going to look at the observations that are close to me in a certain area, and only use those to calculate the weights. You could do that. So you get a local weight, right? The weights become locally varying. And however, I tried this years and years ago, and it turns out that there are some real problems. And the problems are actually, why don't I use this? The biggest problem is the resampling. So of course I can do the local weighting, etc., and I can do my update, and I can get, for instance, the following situation, that in this area over here, the weight of particle 1 is really high, so I want to keep that particle, but the weight of particle 5 is really low, so I don't want to have particle 5. But in an adjacent area, I have that the weight of particle 1 is actually low, given the observations in this area, and the weight of particle 5 is actually quite high. Now, of course, after I've done this data simulation, like I said, I'm going to do this sequentially. I'm going to propagate the ocean state forward in time again, but I have this sort of discontinuity here. So here I want to use particle 1, so ocean state 1, and here I want to use ocean state 5, and yeah, there's a discontinuity between these two. So we have to do some smoothing, etc. It becomes really messy, and and so this is a problem that's not solved yet. We can do some smoothing. It's quite artificial. There are all kinds of issues. If you're not careful, you throw away all kinds of interesting dynamics because you make things too smooth, etc. And the other issue is that if you think about this, the size of this area is actually determined by the physics. The physical correlation length scale of features. Think about, for those of you who know about length scales of Kelvin waves, for instance, in this ocean area. And so this area cannot be too small. So typically it will mean that there will still be too many observations, more than 10, in each of these areas. So we still have the same problem as before. The localization alone will not solve our problems. Having said that, people have pushed it, and I'm giving you an atmospheric example here just to sort of show what we're doing and how things are pushing things. So with very careful smoothing, etc., and the people have been modeling this kind of convective storms. So this is in the atmosphere. So this is a high resolution model, and what you show here is the reflectivity, the radar reflectivity from a radar on the ground, and this is the signal that it sees, and the come on, you can do this, and what do I want to say? Okay, so this is a horizontal cross section, and this is a vertical cross section of that storm. High reflectivity means a lot of droplets and rain, etc., and high nonlinear dynamics, etc. so they've done particle filters on this system, and it's a really hard problem. Lots of observations, and it's not trivial. And they use this thing called localization. And one of the results, I'm just showing you one thing here, actually two things. So this is these first two plots are the what happens at the freezing level at about 4 kilometers. In this storm, it was about. Is that me doing that? Okay. Anyway, so this is sort of state of the art ensemble Kalman filtering. That's sort of the thing that most people use nowadays in the geosciences, really, or reservoir modeling, etc. Ensemble Kalman filter, ensemble Kalman smoother. That's what people use. And this is this I should have said that this is the error or the bias, as they call it, in the water vapor, the amount of water in the column, and this is so this result ensemble Kalman filter. This for the particle filter, you see that the errors are much smaller than over there, and this is at a different height level. I don't want to say too much about it, but you can see that if you really push really hard and there's a lot of tuning, etc., going on in these particle filters, then you can beat the standard methodologies. So that's good news, but it just we tried to use this code on another problem and it completely failed. It's very sensitive to specific problems, so it's not, in the end, not really that useful. So the other method that people have been pushing is exploring proposal density, and the idea is just very simple, that so n now here is a time index, so we want to know, to represent this probability density at the posterior time n, and of course we can just write it down and push it back in time, where now here we have the prior at time n minus 1, and this is just the transition density to move from n minus 1 to n. Now suppose we have a set of particles at time n minus 1, as I had this sum of delta function, I can just plug it into the equation. And if I would know how to handle this, then there would be a consistent story. But somehow my fingers are also too. Anyway, so what we get, so when we plug that in, then we get that the posterior is just the likelihoods over here, and we get this sum of transition densities. And we know that if we just use the model, then we the standard model with this random forcing. I don't want to talk too much about it, although it's a very interesting problem in itself. In the standard particle, you just draw from this density. For every particle, you just make a draw, and then you calculate, you evaluate the likelihoods. And now we're going to do something else. We're going to draw from a different density. And before we do that, I just write this combination here in terms of in this way. So I combined this likelihood and the transition density using Bayes' rule. I get here one transition density with unknown xn, and this just becomes a constant only depending on what happened the previous time. Just Bayes' theorem, nothing special. The good thing now is that there's only one term now that depends explicitly on where I put my particles at time n. Okay, now what we're going to do is we're going to multiply this expression from the previous page by a function, a probability density q, and we're going to divide by the same q. And as long as the support of q is the same or larger than that of p, then I'm fine. I can always do this. And what is this q? So this q will be a transition density. It will be a different way to move my model from time n minus 1 to n. So instead of using my normal model equation, I'm going to use something else. So before we do that, however, we can already start looking at what the weights will be if we play this trick. And so how do we calculate the weights? Well, the weights of each particle depend on the particle index and the position where I put that particle. So my starting point at n minus 1, that's sort of representing this I, and the new position of the particle, that combination. And I can just write down what it is. If I make a draw from this density, so I use the different model, then this whole thing here will be my weight. So that's what it is. And so the weight is the function of I and the position xn for each particle. And of course I can use this expression for total variance and to actually calculate that weight. And that's what I'll do, not in all details. So what a standard choice is to assume that this transition density has this form. So for each particle n, it depends only on one previous particle. And one also chooses the probability of choosing a certain point, a certain particle at the previous time now, is 1 over n. So I'll just take each of these particles. And it turns out, with these two choices, that there is an optimal Q. There's a best Q, there's a best proposal density to move my particles from time n minus 1 to n. And that is this thing over here, and it's called the optimal proposal density. And it's best in the sense that the variance in the weights, which you can just calculate, is minimal. So for proposal densities of this form, you can't do better than this. And it turns out that, again, for our problem, these weights, they're all over the place, and the whole thing is degenerate. It doesn't work. So the optimal proposal is just not good enough. So if this would really be optimal, I could go home, but luckily it's not. And I give a simple counterexample. Again, here we have our expression for the posterior PDF in terms of the weights and the transition density. And instead of actually choosing the index I with equal probability for each particle, I'm going to maybe another way. I'm going to choose it this way. And what that means is that I'm going to see this. Wait a minute. I have here a density which I just see as a mixture density. This is just a mixture density. It's just a sum of density with coefficients. These are the coefficients. Now I know how to draw from a mixture density. One way of doing that is I'm first going to draw, look at these guys and decide which mixture density I'm going to choose, which of these PIs I'm going to choose, and then I'm going to make a draw from that. So if you do that, then you first draw this, and then you draw your xn according the I here. Sorry, the I over here corresponds to the one that you did draw there. And when you do that, then you see that the variance in the weight is 0. And so it is possible, very simple, to generate equal weight particle filters. It's not difficult. We can just do it. It only turns out that the ensemble that you get from this is actually not that good. And the reason is that, as I said before, these weights are actually not, these weights are the same. They're not behaving very well. The variance is large, meaning that by drawing from doing these draws, I keep on drawing from the same. I keep drawing the same coefficient, so all my particles will come from the same transition density. There's if I don't have enough samples, then I still have the problem. But at least the variance in the particles can be made 0. Now we need to do better, obviously, because this is still all not well. So what can we do? So we came up with the following idea. You can just look at the weights. How the weight behaves as function of where you are in state space. This star should be an n. So think about the horizontal axis is my state space, so my billion-dimensional space. I'm going to move my particle around, and wherever I put it, I get a different value for the weight. So each of these curves here. So this one would be the curve for particle 1. So I start at particle 1 at time n minus 1, and dependent on where I put my particle at time n, I get a different weight. So for each of these guys, I get a curve like that. Of course, I'm not going to calculate it, but this is just in principle, it's there. Now, what we're going to do is we're going to set a target weight. So I have a recipe that's down here on how to calculate the target weight. I say, okay, I want 80% of my particles to be able to reach that target weight. And what that means is that for each of the particles, I just going to move them around in state space such that they get exactly the target weight. So think about particle 1 here. You see that there are 2 points. Either I put it over here, or I put it over here, and to get the target weight. Of course, this is a billion-dimensional space, so that's not just 2 points. There's an infinite number of points, so you can that gives you the target weight. So you have to come up with an algorithm to choose something, in theory it doesn't matter what you do, and in practice you have to choose wisely to make things more representative of the posterior PDF, because remember, you only have a very small sample, so each sample has to be good in some sense. we can talk about that, what that means in the end. Anyway, so I can do that for each of these particles, but you see particle 5 has a problem, because wherever I put particle 5, it can never reach a target weight. And so particle 5 is just out for the moment. I just kick it out. And but in the end, I will resample all the particles, so then I'll bring it in again. I can always do that. So what happens is that that now I said the number 80%, right? So if I have 100 particles in total, then 80 particles will have exactly the same weight. And I can of course do my same trick on the variance of the weight. I can calculate all that, blah blah, and I get this expression for the variance of the weights. And this variance of the weights is indeed larger than for the optimal proposal density. So we're still within theory, right? We didn't cheat in any way. But the thing is that still I have made sure that it's not one particle that has a weight much higher than all the others. I've made sure that 80% of my particles have a have a weight higher than the others. So by construction, this is never degenerate. And however, of course, there's a price to pay. When I push the number of particles to infinity, so this ideal case, when I just do that, the scheme is biased. It's easy to show that I'm not converging to the true posterior PDF. And but of course, that's not the relevant limit. And I don't want to offend the mathematicians among you, but I really don't care about what happens when n goes to infinity, because there's no way ever that we're going to do that for these kind of problems. The computers will never be big enough. There's an easy calculation to show you that there are just not enough atoms in the not enough atoms in the universe to do these kind of calculations. Easy to show. So we have a bias, even for small n we have a bias, but of course that bias should be compared to the Monte Carlo error that you have anyway, and it's really the trade-off between these two. So as long as the bias is smaller than my Monte Carlo error related to the small ensemble size, I think I'm still okay. Anyway, we use this on the climate model, just to give you an example, and this is just to show you a picture of the climate model. This is the correlation between atmospheric zonal flow and oceanic meridional flow with this difference in the northern sun hemisphere. If you know about the dynamics, you understand this picture. Just to show you something instead of just this kind of plots. And what I show here, this is time, and this is temperature at a certain grid point, and this is another grid point, and the yellow lines here are, I think 42, I don't know exactly the number, that order of magnitude. So order 50, let's say. 50 prior ensemble members, and the blue ones are the posterior ensemble members. And the red, if you can see it, there's a red line here that that tells us the that's the true. So and this is an artificial experiment, no real data, but just data generated by the model itself. So just to check methodology, that's the starting point. And so we seem to be able to do a good job. Now we looked at it more carefully, and it turns out that it does a reasonable job, but we should definitely do better than what we do here. This is not the end of the story. And then we came up with the following, that we are working in these extremely high dimensional spaces, and the question is, of course, is there something that we can explore in these high dimensional spaces? Can we use the fact that we are in these high dimensions? And there's something funny happening in high dimensional spaces, and it's called concentrational measure, or the typical set. And I'd like to just show you, give you an idea of what's going on there. Okay, before we start, remember each particle does not represent a probability density, but it represents a probability. So if I have 100 particles and they all have equal weight, then each of these particles represents a probability of 1 over 100. So they represent a probability mass. So if I think about that in the following way, so here I just draw in my state space, I draw the posterior PDF, and this is the distance from the mode. Let's assume I have a unimodal, maybe a Gaussian, right? It doesn't really matter for this argument. distribution. So this is the distance, so that's the one-dimensional feature, so this indeed is the whole picture. Now, like I said, the particles will not concentrate at high probability density levels because they have to represent probability. So where's the probability? Well, then we have to multiply the density with the volume, of course, that you represent. So this is my volume delta x, and that, of course, in high dimension spaces, well, that just grows dramatically. The size of a grid box. What is it? In state space. Yeah. So to get the probability, we have to multiply these two. So this is where the probability mass is. The probability mass is concentrated away from the mode, and so this is where my particles should be. My particles should not be at the mode. They should be somewhere here, because that is where the probability mass is. And to see how that works, and these figures are stolen from Michael Betancourt. So let's have a look where the probability mass is. So this is the same plot, the posterior PDF here. This is a one-dimensional case, and I think he did draw about 100 samples from just a one-dimensional Gaussian, and you see how they are distributed. Okay, and now we're going to do this for 10 dimensions. Same thing. I should say that I normalize this axis with the square root of the dimension of the system, so that we so it's a distance divided by the square root of 10. And then, I'm sorry for the colors, but it's darker here. So what you see is that we start out with a distributed over the whole area more or less, and then now we get the hump here. So if I draw from these samples, I see that they're pushed away from the mode. And if I go to even higher dimensions, 100 dimensions, you see there's even sharper peak, and for 1,000 dimensions it becomes much sharper, and you can imagine what happens for a billion dimensional space. There's a very, very, very sharp, thin, I should say, hypersurface where all the probability is. So you have the mode here, and there's no probability mass in the mode at all. It's all away from the mode at a distance the square root of the dimension of the system, if everything is normalized, etc. properly. So can we explore this? So actually, we sort of know a bit more about these systems than we should think. Can we explore that? Now suppose this is my posterior PDF in these vague gray lines, and this is the so-called typical set. So this is where the probability mass is. And of course I don't know how to draw this in a billion dimensional space, but you can imagine with this two-dimensional picture what's happening. So my particle should end up somewhere here on this yellow curve. And just to give you an idea again, so if you think about when we run Ensemble Kalman Filter, we often say, well, it's a Gaussian distributed, everything is Gaussian distributed, and so the mean is our best estimate, etc. But the funny thing is that, this blue cross here. So suppose I manage to get Ensemble Kalman Filter and get my particles on the typical set, then the mean will be somewhere here, and that ensemble mean is just not on the typical set. So it's a very atypical state in that sense. And the same for variational methods. Variational methods try to find the mode of posterior PDF, and we just shown that that would be a very unlikely particle. Meaning, if I just draw a particle randomly from this distribution, I would just never get the mean or the mode. It wouldn't happen. Anyway, the question, of course, is but where's the truth, right? So where should we be? With this typical set, we know that the mode is unlikely in terms of probability. Where's the truth? And so, if a particle filter works well, then the idea is that each of these particles could have been the truth. So each realization is could have been the true evolution of the system. So that means that both the truth and all my particles should come from they're drawn from the same PDF, the prior PDF, and they sorry, I want this to happen, So the truth lies on the typical set of the prior. If the system works well. A lot of assumptions here, but it should be there. And if you look at the likelihood, again, we have a measurement of the truth with the uncertainty. So we know also that the truth will lie on the typical set of the likelihood. So it'll be the same thing. So where's the truth will be at the cross section of these two. So these red lines here, so if this is the likelihood, the green thing, then this is my typical set for the likelihood, and this weird thing is the typical set for the prior, and at the intersection of these two, that's where the truth is. So we actually know that. But the problem is the following, that I've assumed here, of course, that I can represent everything in state space. Of course, observations are in observation space, but let's gloss over that now. We can talk about it more if you want to. But the funny thing is, if you think about where the posterior is and what a typical set of the posterior is, you find that typically the truth is not on the typical set of the posterior. And that's a bit weird. And you can easily see that in the following way. Suppose my likelihood and my prior are exactly the same Gaussian. And then we know they both have a typical set with a certain distance from the mode. And then, but if I multiply these two, then I get a sharper Gaussian. And the typical set of that posterior will be closer to the mode of the posterior. So I know the truth is on the typical set of the likelihood and the prior. These typical sets would be the same in this simple example. But the posterior has a typical set that's narrower, that's closer to the mode of the posterior. So it's not on the typical set of the posterior. So none of my posterior samples is actually representative of the truth in these high-dimensional systems. And that's very counterintuitive, and I just don't know. I must confess, I don't fully understand what that means. Neither you.
I'm a bit lost. So the prior is a probability over x.
Yep.
And so that's, but the likelihood
is
a probability over y, no?
Okay, no, so let's
it should be a picture like this, no? It shouldn't be on the same axis.
Okay, so let's assume that we observe the whole system. So then of course the likelihood, I can look at the likelihood as function of x of the state. The observations are given, so I know that.
But then this set, this typical set makes no sense as a function of x. The typical set is a notion of as a function of y for the likelihood, no? What's the typical?
Yeah. But the thing is, okay, it's a good remark, of course. So we have the likelihood is p of y given x. Okay. Now my observations are given, so this is a function of x. Mm-hmm. So I can just look at what is this as function of x, and I know that y is x plus some error, right? And so, like I said, I observe the whole system and I observe it directly. Let's take that example. So, so if I look at my likelihood in x space,
what I'm trying to get at is it's the volume of x that you're multiplying with, which is the same volume for both x's.
Yeah.
The special set comes out because you're multiplying a volume with a probability. And so it's the same volume that you're multiplying once with that probability and once with that. So I'm not quite seeing that picture.
I see your problem. I think it's okay, but I need to think about that. Okay. I think we're okay because we're looking at probability density functions in state space. Okay. So I think we're okay. Okay. But the thing I want to draw here, so this is my observation, and the observation error is there, and so my typical set will be, yeah, somewhere there.
The definition of the truth, is that an optimal particle? What's the truth?
Okay, so the truth is the thing that generated the observations. So the truth, so okay, this is sloppy. No, it's not sloppy, I'm summing up. So I say that the observations are measurement of the truth, xt plus some error. This is how I generated my observations. Okay? So that's the real world. I don't know what it is, but I know something about it because of the observations.
Sorry, I'm gonna hook you. I'm gonna continue to hook you. The typical setup. So this picture that Michael made is basically trying to get around the image of that probability of x doesn't matter. It's the probability of x, the weight that comes from probability from the volume that really kills you. But if I'm doing the Bayes rule, is I think what you're saying is you can't follow the Bayes rule through this argument. But you can, because the probability of x times the probability of yx is still the same as the probability of x given y, and then you multiply with the volume. It's the same likely set, in my opinion.
No, so I see what you mean, but I don't think it's true, because what the thought experiment I tried to sketch with my hands was clearly not very successful. If my likelihood looks like this in state space, and my prior looks exactly the same, then Bayes' theorem tells me I should multiply the two, so the posterior PDF will be this.
Oh, I see. No, I get it. Okay.
So the typical set will be somewhere here for the posterior, and it will be somewhere else for the. So that was the idea. I'm sorry, I glossed over this a bit. Anyway, so this is just actually an aside, because in Bayesian or Bayesian inference, we are not interested in the truth. We're interested in the posterior PDF. If you're interested in the truth, you should do something else. I don't know what, but I think no one knows. But posterior PDF is what we're after. So no matter what happens here, we need to try to find, to place the particles on the, actually that's what I'm saying here, we need to find, put the particles on the typical set, because that's where they should be, and they also should have equal weight. And that's the tricky part. So we can come up with particle filters that put particles on the typical set, and the optimal proposal does a very good job at that. But the problem is that the weights are just horrible. So the idea is the following. Can we find a Markov chain? So suppose I use first the optimal proposal density to push the particles on a typical set. And then I'm going to try to find a Markov chain that will keep me on the typical set, but of course I move the particles, so I change the weights. So find a Markov chain such that I keep on the typical set and change the weights of the particles such that they become more and more equal. So that's sort of the idea. And I haven't got full proof of that, but the intuition is, and it's not only my intuition, of a lot of people, but there is no solid proof as far as I know, that if you just do Hamiltonian Monte Carlo, it actually keeps you on the typical set. And so we want to use HMC methods to keep us on the so bring you to the typical set with a good particle filter, and then stay on the typical set but move around to change the weights such that in the end the weights are okay. And so we've been playing with this, and I'm not going to show you any results because there's no time. Yeah, we're trying to push this to bigger systems, and yeah. So this is. I'm just, again, like I said, I'm giving you some of the thoughts that people are having and what they're trying to do. So the last thing I'd like to talk about is this optimal transportation. So the idea there is different, and some people might say this is not really a particle filter, but anyway. It uses particles, it uses model states, and suppose these are my prior particles. And the only thing I want to do is I want to transform these particles somehow to make them particles of the posterior. That's what I want to do. I want to find a transformation that brings them from here to there. And so again, standard particle filter would not change the particles, it just calculates their weights, and by weighting the particles they become particles of the posterior. The weighted particles are particles of the posterior. We've seen that doesn't work. So now let's not do that. You just say, okay, for each of these ones, guys, I want to find a transformation that brings them somewhere else. And and there is this thing called the Ensemble Transform Kalman Ensemble Transform Particle Filter that tries to do this in one step, and I think it's not a good way to go. We have to come up with a smooth transformation in artificial time. We want to slowly move with small steps from there to there. And remember, this is all at observation time, right? So it will be a transformation in artificial time. Okay, again, this is the expression that we have for the posterior. This is the best expression that we have at this moment. We have particle time n minus 1, and we can write the posterior indeed in this way as a as a continuous PDF. Now, since I have only 100 particles, you might say, well, this is not very accurate. So the problem is, when you do the sequential Bayesian inference, you do not know what the posterior looks like. If you do a static problem, then quite often you do know what the posterior looks like. At least you can write down the equation. You cannot sample from it, but you at least can write down what it is, or you know what it is, some way or the other. And here we just have a very poor approximation from it. But anyway, so the number of particles is small. We have this problem with the observations, etc. But I think we can actually solve these problems quite efficiently, and I'll come back to that later. The first thing what we do is we have to define a distance between the prior set of particles and the posterior set of particles, and we use here the KL divergence. And so what we're going to do is we're going to find the transformation. So X is my state, as is one particle, let's say, and I'm going to make a transformation. So I'm going to move it around such that, and I do that for all the particles, such that the PDF that they represent becomes closer and closer to the posterior PDF that I want to have. So I have to, so if this is my transformation, then I have to find the gradient of KL divergence in that direction phi. Anyway, so these are actually details. I don't want to spend too much time on it. And so I just say you can come up with an algorithm that does this. Although you have to think about, you have to restrict the search space, of course. There's an infinite number of ways you can move around, and what we do, we use here this reproducing kernel Hilbert space, and it has this property. So phi is in that space, and then if I do that, then I can write down what this gradient is in terms of these reproducing kernels, which typically we assume are some sort of Gaussians, but again, we need to put much effort into this. Again, we're talking about ideas here. But anyway, we can come up with an iterative scheme in which J now is the iteration that slowly pushes my particle from prior to posterior. And just, until the KL divergence is 0, right? Yeah. and the weights plain overall here, there are no weights. Okay, so how far did we get with this? Lawrence 63, three-dimensional system. I can do that. If you look at time, this seems to be okay. So we have three variables, x1, x2, x3, and what is it? The blue lines are this is my prior, and let me see. The black line is the posterior, and I know it analytically, a simple system. And the red line is what we get out of our transformation method, and we used, I think, 50 particles, something like 50, and we used some kernel dressing to get smooth pictures, right? So we can use it for the standard SIR, sequential important resampling filter, that the vanilla one, and we can use our what's called variational mapping particle filter. Anyway, so what we see is that in this third variable, the standard particle filter has even with 50 particles in a three-dimensional system, observing, I think we observe all three variables, the standard particle filter is just not doing the right thing. It's just struggling, and we can do this. And of course we can do this. We can look at it as 2 dimensions, so these are cross sections. This is x1 and x2 and etc. The contours, the blue contours, are the true posterior PDF. The dots here, these are the priors, and here I use a standard particle filter step, and here I use my filter, and you see we have a nice coverage of the posterior PDF. Note that a typical set doesn't play a role in a three-dimensional system, right? So we don't see that here. Okay, the question then is, so this is how far we got, right? It's a new method, and we think it has great potential because of this. What can we do in high dimensions? Because the problem is we have a very small number of particles, and we have a lot of observations. And we know that this combination is just killing the whole thing. But we can, in this case, we can do localization on the posterior. So we can get a pretty good estimate of this posterior by localizing this whole thing. So for each grid point, I'm only going to look at observations that are close to me. And there is no restriction on the physics in this case. I cannot break physical balances or whatever, because I'm only trying to represent the posterior as good as possible. So I can make the localization error really small, so that I only have a few observations in each area. So I can use, so these weights are not degenerate in each area. So I have a sort of a very, I just get and in each small area, I have, if I do it with 100 particles, I have 100 particles in this very small domain where I want to represent this PDF. So what this localization does, right? It increases the effective number of particles, because suddenly I have a whole lot of disjunct, instead of this billion-dimensional state space, I have a very large amount of very small problems. They're actually quite small. I'm not going to solve any of these problems. Again, I'm only going to use it to get a smooth and good representation of this one. And like I said, with a better weight balance, because we only have a small number of observations in each of these areas. So this is what we are at the moment implementing in a bigger, more realistic system, and yeah, we hope that will give us something useful. So to conclude then, when we look at the geosciences and nonlinear data simulation, didn't talk about the standard Ensemble Kalman Filters, etc. stuff, but really pushing the nonlinear limit. We've seen localization is not enough. Just doing localization is not enough, because we have to then do we have these sharp gradients, have to do the smoothing, and it's just too sensitive, and it just doesn't really work. The optimal proposal density, which some people say, okay, if you can't, for these big systems, the optimal proposal density doesn't work, so particle filters are out. That's clearly not true, right? We can do better than the optimal proposal density. Forget these bias statements. They're a bit. They're not that. Depends on what you call bias. Anyway. Anyway, so but we've done better, and this mapping. Yeah, we can do good things. The real thing, of course, is we want to know how accurate we're doing. How good are we doing? And that means we really need to understand the small n statistics. So the convergence rate of Monte Carlo going as 1 over the square root as a constant over the square root of the number of particles is not good enough. We need to know what the constant is for the different applications. So, and I know there's some people out there really try really hard to try to figure out what these constants are, and that's exactly what we need for any geoscience applications with this kind of methods. And last thing here, what about emulators, can we use them in this kind of problems? And of course the problem here is the prior is high dimensional, the posterior is high dimensional, and I cannot just concentrate on part of the state space, because I have to generate a full state space again to propagate the whole system forward again. So I don't see how I can do some sort of dimension reduction here. And last thing about multi-scale models, the problem is in this kind of geoscience models, like the ocean, the atmosphere, is every time when you increase the resolution, you do not only get smaller scales, you get new physics. The physics changes. For the atmosphere is very clear. Suddenly you resolve more of the clouds, and so you resolve more cloud processes. So the physics changes, and so there's no convergence when you increase the scale, decrease the grid size. There's no convergence because the physics changes all the time. And so multi-grid methods, I'm not sure. So we should of course talk more about that, Rob. But anyway, so that's all I had. Thank you very much for your attention.
I'm trying to relate what you explained to the talk of Henry Wynne this morning on design.
Yeah. That's a good one.
Because basically you have a set of points, an empirical measure if you want, and you want to optimize it in some way, but what I don't get completely is what is the criterion that you want to maximize.
I have no answer, and the thing is, I want to represent the posterior PDF as good as I can. So I mentioned at the beginning, and I come back to that. So what exactly, what do I mean by that? And the answer is will be no doubt when this evolves further. It depends on what you really want to know about the posterior of the PDF. If you're just interested in the mean or the variance, etc., then you can do things. But the mean and the variance of what variables or what process or whatever, and because clearly with 100 particles, I mean, I can do a lot of talking, but in the end we know that will be a very, 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 very poor representation of the posterior PDF in whatever sense. Maybe I can look at the marginals and then I can do something.
But it looks like we know the criterion for one point, but what you want is something joint over the whole family of particles.
Yeah, sure, yeah, true.
So probably there is something here to formulate.
I guess so. I just don't know. You should definitely talk. Very easy.
I have a question about this last idea that you presented. That, I mean, you probably know anyway, but I was a bit puzzled because this sounds exactly like the Stein variation gradient descent method by Liu and Wang. Okay.
Yeah. So the difference is that they use it in steady state formulations, and we have now just put it into the sequential framework.
I see. That's for each individual step of your sequential estimate, it's exactly the same thing, essentially.
I haven't seen that.
No, I'm just saying.
Oh, okay.
I'm asking you. For each step in your sequential Monte Carlo, you're doing essentially their algorithm. For each one single time step of your
and if you look at
it, pseudo time then anyway, so it doesn't.
Yeah. So the thing is, the essential thing is that we need to have a probability density here. So that means that we have to include errors in the model equations, which is a big problem in itself. And the other thing is that we have this poor man's approximation of this whole thing in high dimensions, but the localization I think will sort that. So there are all kinds of things there. And the other thing is, of course, when you look at these kernels, they just use a Gaussian, just a standard Gaussian. And obviously we have to put here covariance information between the different variables. So we have temperature and pressures, different units. So you have to be careful. So you have to put real effort into generating these reproducing kernels. But it's the same method.
My PhD student is working on that.
Yeah. No, this is shooting. Lots of people work on it. I know. Yeah. I should have mentioned their reference.
What about injecting Ensemble Kalman filter ideas at this step with somehow annealing?
I mean, even if you go back, you can think about, okay, let's do the Ensemble Kalman filter. Use the Ensemble Kalman filter as a proposal density. So first you use the Ensemble Kalman filter, and then do the particle filter on top of that. But it's easy to show that unfortunately doesn't work, because the Ensemble Kalman filter is worse than optimal proposal. But that's a detail. But at any stage, of course, you could bring in standard methods from the geoscience community. So, for instance, we use ways to calculate things in an efficient way to keep it all in ensemble space, never go to the full space. Covariances, for instance, of these systems, we cannot store them. They're too big. So there's no computer in the world that can store the covariance of such a. So you have to. All these tricks we use, and indeed you can. Like you said, you can use Ensemble Kalman filter steps as to push things in the right direction. But the problem is with Ensemble Kalman filter. If you use an Ensemble Kalman filter that works here, you have to do localization, but that will be sort of the bad localization in the sense that you can destroy the balances because I didn't really talk about that. But if you do localization and then you don't propagate. The thing is, you want to keep. How do I say that? If you look at the updates that you get here, the smooth update, they all of them are proportional to the error covariance of the model error. And that error covariance of the model error has a physical structure in there. And that means that that all of these updates they sort of retain the physics. And with the Ensemble Kalman filter you have to be careful, and you can break things, etc. But yeah, there's much more to say than I can just come up with now.
I want to go back to the concept of typical sets.
Yeah.
Still have a bit of trouble with that. So I've heard this concept before as high-dimensional Gaussians being like soap bubbles. They have almost no mass, but on a thin spherical shell with some fixed radius.
Yeah.
And as this seems to work is you split the whole space into spherical shells, and you look for that shell which has the highest probability mass.
Yeah, in principle you could do that, right. I guess, yeah.
So, but isn't it a bit unfair because you're comparing subsets which have polynomially growing Lebesgue measure?
Mm-hmm.
So you're not actually just comparing shells, but you're comparing a shell with very small Lebesgue measure to some with astronomically high Lebesgue measure. So if you have growing radius, then of course you'll expect that until some point you'll have growing probability mass until finally the exponential decay of the Gaussian measure will kick in. So,
so let's put it this way: if I'm in a high-dimensional Gaussian, if I make you can do it on your computer, right? So 1,000-dimensional Gaussian, just independent. For instance, just keep everything simple, independent in every direction. You just do random draws from that Gaussian, and you'll see that the length of the vector is always as a 1,000-dimensional square root of 1,000, so 33. And the uncertainty there is a half, if I'm not mistaken. And if you go to billion-dimensional space, the uncertainty is still half. So the spread in the distances from the mean is still half. So the typical set, I mean, it's there, and you can just see it when you draw randomly. And you can write down the equations, and you see immediately what's happening. This is just a law of random numbers that you when you add a sum of squares, you get a chi-squared, and when the number sum is large, actually it doesn't even matter, and you know the mean and the variance of that. That's just what it is.
Just very quick follow-up question. So I completely agree with what you mean, but just to mock this procedure, let's take a one-dimensional Gaussian measure and split the whole real line into a very very thin interval around 0, around the mean, and the whole rest. Then almost all the probability mass will be on the whole rest. So the typical set is not centered, but it's like two modal or something. Because you're comparing two sets of very different Lebesgue measure, and that puts the probability mass in favor of this set.
Yeah, so the typical set is sort of, I don't know the exact definition, I should have looked it up again, but it's sort of the minimal set that has a certain amount of probability in it. So we say, okay, I want to cover 95% of probability, and then, so the typical set is dependent on the amount of probability that you want to include in that. And then, so the typical set is that thing. And of course, when you have multi-models, you have to be careful.
Because I think you're asking a technical question and you're trying to ask a general answer a general question. I think there's a much more technical question he's asking, nothing about the actual things you were referring to.
No.
I might misquote you, but I think what you're answering is he understood. Okay, maybe we can take that to the coffee break and thank the speaker one more time. Come back in half an hour, I guess. Yeah, at 4 o'clock.